I will talk about theories about numerical weather prediction. Okay, this is a scary slide with a lot of equations there, but stay calm. This set of equations is called the governing partial differential equations for describing the physics model behind. The physics model involved fluid dynamics and thermodynamics. And for the real world, apart from the dry atmosphere, there is moisture, which adds a lot of complication. So there are equations about moisture. I will explain more in the next slide. And for predicting the weather, you need NWP model. And the gridding in the model is a topic we learned in this course. There are many models in the world, and I just pick an example, which is from the United States. It is called GFS, the Global Forecast System. And this version is using a model or a dynamical core, and you will know later, which is called FV3, finite volume Kip model. And this model actually supports quite a number of different gridding methods. But you will see many people use rectangular grid. In some way, in this way, it is called a keep the sphere. It is something like a balloon, and then you draw a rectangle on the balloon, and then you blow it up to become something three-dimensional. And then this is actually a curved surface, and then this is something like a rectangular grid on a spherical surface. And there is something like adding a high-dimensional grid inside a coarse resolution grid, and multiple level of gridding. And then there is also this one, stretched grid, supporting variable resolution with some form of transition. So in the world, there are a number of different NWP models and gridding methods. For these equations, you just have to notice the equal sign, and then the left-hand side, and the long right-hand side. And then there are several equations, 5 here. Summarizing what they are, the equal sign means something has a relation to another thing. And for these governing equations, the left-hand side is mostly rate of change of something. If you know calculus, it is expressed as a derivative with respect to time. So you see run something, run t here on the left-hand side. There are different things, but the left-hand side is always run something, run t. If you know calculus, why not d something dt? It is because there are multiple variables, and in calculus, we talk about partial differentiation rather than total differentiation. I'm not going to details of the mathematics. All you need to understand intuitively is it is describing the rate of change of something. So what are the something? For dry atmosphere, that include horizontal wind, which is denoted as V, and vertical wind denoted as W, potential temperature denoted as theta, and then density denoted as rho. So you see the run something, run T is V, W, theta, and then rho. And for wet atmosphere, there are Q something something. They are mixing ratio of moisture in different states. QV, vapor state. QC, cloud stage. QI, ice state. QR, rain state. And some some more complicated model will have some more Qs. And you see this, the last equation about moisture. And what are the right-hand side? So complicated. They are terms related to the something itself and some other things. And most important of all, about the location, it's not only related to the location of that variable itself, it's also related to its neighboring position. And in calculus, there are spatial operators. To name a few: divergence, gradients, and curl. You may need not be scared off by this mathematical language. I will explain the intuitive meaning to some of them. So if you see this inverted delta, or I don't know the name, the pronunciation of this Greek letter, it is the spatial operator. For divergence, it will be having a dot after it. And for curl is a few example have curl, maybe this one as a cross product. And then what are these relationships? They are basically Newtonian classical mechanics. It involves conservation of momentum and also conservation of mass. For dry air, this is simpler. But for wet atmosphere, that involves moisture of different states. And then the relations also involve thermodynamics that involve ideal gas law. So this is the relation between pressure, temperature, and the mass of the air, something like that. And also involve conservation of energy and change between heat and kinetic energy. So there is no quantum mechanics, there is no relativity. You are living in a world that classical mechanics already described to quite and good accuracy. So all you need to do is to have some intuitive understanding before using it. And then I need to mention about the grid, because on the right-hand side of the equation, there is relation between the position and its neighbor. So, and in this grid, the governing equations is about pick any point. The governing equation says the rate of change of the physical quantity at this point is related to itself and some other variables, and also have some relationships about the spatial distribution of these quantities. So you may say that this is the field of physical variables, and the field is actually a continuous field. But for a computer program to simulate it, anyway, we need to discretize the space into grid. So the simplest way to discretize the space into grid is using rectangular grid. Here. So these figures are taken from the books by two practical meteorology. And in this course, I very often copy materials from this book out to show you. And this is actually under Creative Commons license, so this author contributes a lot in sharing his teaching material and the whole book. The grid is three-dimensional, though very often when we draw two-dimensional figures. So suppose what you are seeing is one three-dimensional sketch. A grid cell is a three-dimensional one, and its stack up vertically. And on the horizontal side, it is also divided into grid cells. And in the second figure, it shows how we solve these governing equations. For each cell, they have its coordinate, and there is a value for each cell. For example, temperature. There will be one floating point number representing the temperature, the average temperature of this grid cell in the computer program. And then the computer program needs to calculate the change of the physical variable in the next time step. So this is the way we say it. These are the resolved variables, one for each grid. And then for the resolved variables, we calculate the process. Say in this example, the neighboring cell is hotter, and the wind is moving faster, and it contains more moisture, just like this symbol say. And then some physics process happen all around the world. And for the other side of its neighbor, say the physical process results in the neighbor being colder, and then the wind moves slower, and then the moisture becomes less. So the change of these variables happening in this cell is to be calculated by the computer program. We call it the dynamical core of the NWP. So this is the book I shall mention before continuing. The material I have taken here is from chapter 20. And I suppose during this course, you also have to read this chapter by yourself. And many other chapters are great. And so I show the whole page. Let me go on. I shall mention not in this lesson, maybe lesson 3. There are physics processes that are not resolved by this spatial discretization. They are called physics parameterization. What should I say? I should say that as the grid cells cannot resolve it, but the real world has these processes, they have to be parameterized. So in the partial differential equations, there are source terms and sink terms, or they are sometimes called the forcing terms. If you go back to the equations, you will see these forcing terms. So for physical processes, they have short scales and are not resolved by the grid. Somebody needs to devise some mathematical scheme and then to estimate the effect in a bulk and then put to the source term or sink term to represent what happens within the cell. Okay, this is a brief introduction.